Hello, I'm Liao. In July, I went to a conference in Beijing to give a talk in Chinese. I know it's been a few months since then, but I think the content is really nice. It's quite unique and I especially created for the conference. And because if it's in Chinese, you guys don't not able to see them. So I decided to translate the slides and the content in English and upload them to YouTube. So this is the content. Here we go. Hello, I am Li Hao. The talk I'm going to share today is the new wave of frameworks. What can we learn from compiler-based frameworks? As I mentioned, I've shared this in the Beijing Xitu 开发者大会, which is the Beijing's Xitu Developer Conference. And so I have converted all the slides in English, and here we go. So before we start about the talk, let's take a look at what are compiler-based frameworks, or what is the current frameworks landscape, right? How does it differ from the frameworks that we currently know of? Well, currently, the mainstream web frameworks that most people know of are Angular, React, and Vue. They each have a sizable market share. To be honest, I don't know much about Angular, and I spend most of my time with React and sometimes a little bit of Vue. Okay, so the main difference that I try to summarize here, if I'm wrong, just pardon me. The main difference from this generation of frameworks compared to their previous generation is that Angular, React, and Vue allows developers to declaratively describe their UI. We only need to care about the current state and how we describe our UI based on the current state. The framework will take care of the rest for us. For example, when a state transitions from one to another, we don't really need to care. How do we use DOM APIs to modify our document from one state to another? But let the frameworks to take care of that for us. So how does the framework do that? Well, if it's not processed efficiently, then the page will freeze and it will impact the user experience. So performance is very important. Well, currently the most optimized way to do that is to use virtual DOM. Whenever a state changes, our page components will re-render and will result in a new virtual DOM. So every state changes, you have a new virtual DOM. And by comparing the virtual DOM from one to another, then we can calculate the most optimal way to do the DOM operations, and we use that to modify our DOM. So naturally, the framework, because of that, our framework will have to ship code to handle all possible scenarios, to handle all different kind of changes, all different types of DOM elements, all different types of listeners, styles, and naturally, the framework code bundle will be sizable. Right? Hold on. Yeah. So since today's topic is about the future of front end, let me introduce the frameworks of the future, right? The new waves. Actually, if you have been following the latest development in the front end world, these frameworks may not be that new anymore. Okay? The main difference between these new frameworks and the current mainstream popular big three frameworks that I call is that they challenge the current assumptions and best practices. Which is, if we could use static analysis to build when building our code, is it possible to reduce the final output code size? And at the same time, is it possible to improve our runtime performance? If the performance and size constraint of the current framework is due to virtual DOM, then I think instead of doubling down our efforts with diminishing returns, like say the React concurrent mode, should we look outside of the box and attempt to use static analysis during build time to get rid of the virtual DOM? Of course, I'm not trying to belittle how amazing the engineering feats from the React team when we work on the React concurrent mode, and there is a ton of improvements before and after React concurrent mode. But today's our main agenda is trying to be forward-looking and trying to see beyond virtual DOM. And the frameworks that we're going to discuss today are Svelte, Solid, and Quick. We'll be going through them one by one and see the explorations of these three frameworks on how to use compiler to reduce the output code size, so smaller code, and also increase the runtime performance. And through that, we're gonna see what we can learn from these explorations taken by these frameworks. We roughly mentioned that these three frameworks, what they have in common is that they use compiler to do static analysis and attempts to trade the build time with runtime performance. So probably slightly longer build time, but with a much better runtime performance. Of course, this attempt would mean challenging the status quo, challenge existing assumptions, and propose new solutions to existing problems. You maybe wonder, using compiler to compile code is not something new, right? And yes, you're probably right. Because if you're familiar with React, you would write JSX, and JSX is not JavaScript. So you have to build your React components. And doing that, you're using a compiler to compile JSX into JavaScript. So the idea of compiler already exists in our existing frameworks. However, JSX is just a syntax trigger from JSX to JavaScript. It is one-to-one transpilation. It does not use static analysis to optimize the final output. Okay, so it does analyze the code and then transform it to the JavaScript code, but it does not do any optimization along the way. So the compiler used by frameworks that we are going to discuss is slightly going to be different from what it is being used by, how it is being used by the existing frameworks. And I believe we have mentioned the word static analysis a few times. But what is this? Well, generally there are two types of code analysis, the static analysis and dynamic analysis. Static analysis refers to analyzing the code while the code is being static, which means it's not being run, it's not being executed. What we usually able to do during static analysis is to see what kind of variables are being declared, whether they are being used at all in the entire code base, and how is it being used in the whole code base, right? So tools like ESLint, if you're familiar with ESLint or TypeScript, they both do static analysis because they don't run your code, but they can analyze your code through that. On the other hand, dynamic analysis refers to analyzing the code when you're executing the code. Okay, so our JavaScript engine, for example V8, will continuously analyze your code while it executes them. So you realize that most of the time you call this function with just a number, then it will optimize your code execution, right? So that is dynamic analysis. Well, I think we're a bit far. Let's get back to our frameworks. So the first frameworks that we're going to discuss today is Svelte. Well, Svelte is also my most familiar framework among the three. So a bit of background. In Svelte has a few versions right now. Currently, it's Svelte 4. And when I think it gained the most popularity when Svelte 3 came out in 2019, because the main tagline is rethinking reactivity. I think there's a talk called rethinking reactivity that also makes me want to learn about Svelte, which is it proposes that we no longer gonna use virtual DOM to make reactive UI, but instead we're gonna figure out the relationship between the variables and your templates during build time in order to generate optimized JavaScript code. And the syntax for Svelte looks like this. It is very similar to HTML. On the right is the Svelte component. You can see that we have a script block, some HTML, and a style block within the same component file. This design is very friendly for non-front-end people like the designers and the back-end engineers, and it's also very friendly to anyone who just started to learn web development. When you define a variable in a script tag, you can use it directly in the HTML template, And the style that you define in the style block will only apply to the elements within the same file. So you don't have to worry about style pollution to elements outside the component. Using a most typical example, the counter component, this is how you implement it in Svelte. Even if you're not very familiar with Svelte, you can easily see how the code works. Right? The main selling point of Svelte is it's very easy to read and write. Here we have a variable called number and a function called onClick. In a template, we have a button and we have an onClick. So click on the button will call the onClick function, which will increment the number variable. And because the number variable is also used in the template, it will be automatically increment as well. So this code is simple and easy to understand. But how does Svelte makes this work? If you put this code into the HTML directly, it will not work. Not just because a button does not have an on::click attribute. It is also because HTML does not support reactivity in its template at all. When you modify a variable in JavaScript, it does not update its value in a DOM automatically. So how does Svelte makes this work? So on the right is the JavaScript code output from the Svelte compiler. Here, except that we try to import some Svelte helper function, basically it's all the code that we need to create this button, including the code to handle what to do when the number changes, how to modify the text content of the button. But I think this image is way too small. So let me zoom in and take a closer look. Let us take a closer look to the compiled code. In the compiled code output, we have function that are dedicated to like create, modify, and destroy elements. So if you zoom in more, for example, we have this function called C, which means create, C for create. So inside this C method, we have DOM instructions to how to create all the elements in the component. And here we can see how it instructs it to create a button element. So the element is a helper function from Svelte, which is shorthand for document.createElement. And similarly, text is also a short for document.createTextNote to create the text content for the button. So the code output for Svelte, we can see clearly that it just directly generates the code needed to build all the elements in this component. So there's no virtual DOM over here. And besides the create method, we also have the M method for mount to mount the elements onto the DOM, and also D for destroy to remove the elements when we no longer need the component. We have P for update. In the update method, we have code to handle what happened when the value of the number changes. So you can see that there's an if condition to determine if the number has changed, and we can update the text node with with the new value. Here we call the set data function, which is basically how we update the text content for the text node. So you might be wondering, how does Svelte generates the updates method? Well, this goes back to the static analysis Svelte has made when compiling a Svelte component. If we try to play around, you can see that if we remove the number from the template, then Svelte knows that there's no more dynamic content in the template. Then in the generated code, the P method has turned into a no operation. Or if we change the code such that you no longer update the number, then number is no longer a dynamic variable. Same thing goes here. P is a no op. So you can see that from the compiled JavaScript output of Svelte, Svelte generates operations to dynamically create, modify, and remove the DOM element. You may have heard the common explanation that updating the DOM is too slow. That's why we use virtual DOM. Well, no. There is a misunderstanding here. The main reason that we are using virtual DOM is not because updating a DOM is too slow. Well, it's because that the front-end frameworks have no other way to determine how to modify the DOM when the state changes, right? So instead of destroying and rebuilding everything, the most efficient way that we currently have is instead of doing the comparison on the actual DOM, is that the framework decides to create a virtual DOM snapshot through state changes and use it to do comparison to figure out what it needs to be done on the actual DOM. But if we can already figure that out during the build time, like Svelte can already determine all possible UI outcome during the compilation, well then it does not necessary to use virtual DOM anymore, right? Svelte can directly generate the necessary code to handle the changes between the DOM into the final output code, and it no longer needs virtual DOM. So now we have explained that the code output that the Svelte generates to update the DOM, but we haven't explained like how Svelte is able to know when we do like the number plus plus, how does it actually triggers the update methods? Well, in order to do that, in the compile code, again, you can look into it. There's one more function that I did not cover just now, which is the instance function. Right? The content inside this function looks very similar to the content inside the script text, except that in the onClick function, we can see there's this line where we have the number plus plus. It's actually wrapped by this function called invalidate. Well, this invalidate function is used by Svelte to trigger the update call. But how does Svelte knows to wrap the number plus plus with invalidate? Well, Svelte determines this through the expression statements that you are using. If you're using assignments, updates, or mutations, then in the example above, Svelte knows that. So in this over here, Svelte knows that name, value, and user will change. And of course, this is not a foolproof solution. Because for example, if you have an array.push method, we know that based on our understanding of JavaScript, the variable array indeed, if it indeed is a array data type, then the push method will mutate the array to update the value of the array. However, in the eyes of Svelte, this is not assignment, this is not update, this is not mutation. So this method, this expression is called a call expression. So Svelte will not wrap this expression with invalidate, and so when you do this, Svelte will not update the DOM. And so a common workaround for this is to assign an array back to itself, because then this statement itself is an assignment statement. Svelte knows that the array variable will change and will then trigger the update method. One more thing to note, that besides determine whether a variable will change, Svelte will also determine that based on the statements, Svelte will also determine that if the variable change will affect the DOM. Right? If you are removing the number from the template, then we know that updating the number no longer needs to trigger the update call, then Svelte will not wrap it with the invalidate function anymore. So to summarize, Svelte will actually list out all the variables that is being declared in the script, and then determine if the variable will change, and also determine whether the variable is being used in template, so it's dynamic. And then with all this information, Svelte is able to generate an optimized JavaScript that you have seen earlier. So we've seen how Svelte uses a compiler to generate an optimized JavaScript with a smaller code output and a faster runtime performance, right? We no longer need code to generate the virtual DOM, and we directly modify the DOM, so it's much faster. So we've done talking about Svelte. The next framework that we're going to discuss is Solid. Solid is an answer from Ryan Caniato for reducing JavaScript code size and improve the runtime performance. Interestingly, the syntax for Solid is very similar to a React functional component. It uses JSX and instead of creating a new templating language like Svelte. And this makes it much more easier for existing React developers to adopt Solid. However, the main difference between Solid and React is that Solid does not use virtual DOM. So using JSX does not mean that you have to use a virtual DOM. If we take a look at an example of a counter component, this is a code for React. It uses useStates to create states and uses JSX to create a button. And this is the code for Solid. Can you spot the difference? Well, if you put them side by side, you almost can't tell the difference. Well, the only thing you can tell is that the solid uses a create signal instead of use states. And I'll explain on the signals later on. I mentioned that unlike React, Solid does not use virtual DOM, which means that the way the function component is being executed is different from React. So in a React component, whenever a state changes, the render method or the function for the functional component will be rerun. This is what we like to call a re-render. The return JSX from that render method on this function is used to create the virtual DOM. And React then compare the new virtual DOM with the previous virtual DOM, reconcile it, and figure out how to update the actual DOM. So new state changes, the function will rerun, return a new virtual DOM, and then we compare with the previous one, reconcile, and then update the DOM. However, in Solid, this is not what happened. Because in Solid, the function will only be called once throughout the entire life cycle of the component, even when the state changes. That's because Solid does not use virtual DOM. But how does that work? Well, let's take a look at the compile code of the Solid component and see what happens under the hood. This is the compile code for Solid, how Solid looks like. Well, the general shape of the function stays roughly the same, except that in the JSX functions, it seems to have some sort of optimization. Right, the first optimization is that the Solid uses the HTML template element to create the DOM elements. So here in this function, we are creating a DOM elements directly. If you look into the template function, you'll see that the Solid uses HTML template element to clone the nodes to create the DOM elements. Unlike Svelte, which we saw earlier, which uses the DOM API line by line to build up the elements inside the component, Solid uses templates. And following on that is to quickly locate DOM elements that is being created from the templates so that we know how to attach event listeners and also to create dynamic elements. So you can see that here in the return function, Solid is returning the elements that is being is creating elements and return those elements for this component itself. Okay, and if there's no dynamic elements in the component, Solid will just return whatever elements that is being created from the template function. So once you clone the node from a template, then that's it. Interestingly, if there's no dynamic elements or event listeners, if there is dynamic elements or event listeners in a more nested element, then the generated code in Solid uses a combination of, after cloning the template, Solid uses a combination of first child and next sibling to try to traverse through the DOM element tree to target the elements. It's kind of like using the shortest path to find the target element and try to attach event listeners on them. Okay, so now we've learned that the Solid uses this is how Solid creates the elements needed for the component. It creates the element directly. It does not rely on virtual DOM to create DOM elements, right? So this is written and this is mounted onto your DOM directly. But we haven't seen how Solid updates this element when we have like dynamic states, right? When the state changes, right? We only see that, okay, now we see that this component will only run once, because once you run it, it will create the elements needed for the component. But we haven't seen how Solid is able to create dynamic elements and achieve reactivity with the component state. Well, the devil is in the details. How Solid creates reactivity is actually to use signals. Actually, here's a small nuance between the code that you write and the code that is being generated. In the source code on the left, we use count with the bracket in the template. We call the count function to get the value of the count signals. So when you call that, this actually returns the value of the signal, and it's being used in the template. But however, in the compile code, what we call into the insert function, I think this is the count. It is not the count value itself, It is the count signal itself. You see that we don't call the count function. But why? Before we dive into that, let's ask ourselves, what is signal? So simply put, in any state, for example, the use states from the use states in React, we actually when the reference of the state variable itself and getting the state value it's actually the same thing. It's actually the same concept. However, for signals, signals is a concept that allows us to separate referencing a state and getting the state value. What does that even mean? Well, stay with me. Let me go through. Well, that's because the signal getter is a function. Okay, so you can pass the reference of the signal around. You can pass this function around through the elements or through your children, through props. You can pass it around, but you're not actually getting the value of the signal yet. It is only when you are calling the getter function. Only calling the getter function is getting the value of the signals. And we only call that when we want to know the value of the signal, right? If we don't need to know the signal, we just need to know that we're using signal. We're going to pass it. We just pass the signal function itself. We pass the reference of the signal. So the reference itself can be passed anyway, but only when we want to get the value, we will call the function. That's when we get the signal value. So this way, actually, Solid has solid with signal, has a more accurate way to determine when the value is being read, when you actually need the value. On the other hand, when we refer to like a state from React, the state variable is the value itself, right? Once you call useState, you get the state, the value, and the state itself is the same variable. So you have no way to know whether a state when it's being read, right? Once you call useState, you get the state, but maybe you're not using the value itself, or you're passing down to a component and you're not using within this component itself. You're passing to your child component and not using this component itself, right? So doing it this way, you have no idea when how or where the state is being passed to and how the state is being used. But for signals, we know, because you only call the getter function of the signals when you want to get the value of the signals. So if we are able to create some subscriptions when we call the signal, like if we're able to listen when the signal is being called, then when the signal value changes, then we can notify all the subscriptions when that happens. Which means that with signals, we are now able to be more fine-grained and more targeted to know when the signal is being used, and we have a smaller scope to subscribe to the signal changes. So how does this got to do with Solid? Well, let's bring the signal back to our compile code. Here we see that the Solid uses the insert function to create a dynamic text element. So we pass in this insert function, we pass in the element as well as the signal reference itself, not the signal value. In this insert function is when we read the value of the signal. And so at the same time, this subscribes to the count signal within the insert function itself. So whenever the value of the count changes, the inner of the insert function will get notified and will then know it needs to update the text of the element with the latest value of the count signal. So the count signal itself only affects or reruns this inner function from within the insert itself, right? So this is how Solid uses signals. You can see that when Solid creates dynamic elements or dynamic attributes, at the same time it subscribes to the signal, such that when the signal changes, it comes back and only updates that small function. That small function will only update the related text or the related attribute. So this kind of signal subscriptions is very small in scope, right? It only does one thing, which is to update the text or the attributes. Instead of re-rendering, the whole component or rerunning the whole component function to figure out, to generate virtual DOM and figure out what is changed. Signal allows us to subscribe in a smaller scope, in a more targeted and smaller scope to update the dynamic elements or attributes. So Solid called this small scope of dynamic update behavior as the fine-grained reactivity. Reactivity, which the granularity is fine, which means only execute the code to update the DOM element only when the relevant state has changed. And instead of rerunning the component functions, re-render the whole huge component subtree and use virtual DOM to compare and determine optimal DOM operations. We only run the functions to update the elements that is dynamic, only for the relevant state changes, relevant signal changes. So if you think about it, through fine-grained reactivity of signals, we skip through a lot of hoops of virtual DOM and directly run the most optimal DOM operations to update the DOM. Then the performance should be much faster than using virtual DOM, right? And for those familiar with Vue, it is actually very easy to see that the signals in Solid and the reactive ref in Vue is actually the same concepts, right? Here I compare the Solid signals API with the Vue composition API side by side. You can see that the both code looks very much alike. Similarly, they only needs to run once to set this whole reactivity up. However, for the composition API in Vue, the refs that is being generated will be passed into the template, into the JSX. So whenever the refs whenever we update the refs object, Vue will rerun the whole component, the whole component's template function, instead of being more fine-grained and more targeted to subscribe the signals only in the place that is being in use. So this is a bit different on how Vue and Solid uses the signals or reactive, but this is what I currently found, and I believe this is something that Vue would be will consider and see how they can improve their final output code, right? So to summarize, Solid uses compiler to compile JSX into code that uses HTML templates, elements to use to create DOM elements. So in a component, you create the DOM elements directly, right? And if you have nested dynamic elements, it also generates like the sum of like a shortest path to traverse the clone elements to find the target element. At the same time, once we created the elements, we also in each dynamic parts, we also use signals to subscribe to the signal changes to have a more fine-grained reactivity to update the DOM. So this is Solid. This is my rough understanding of Solid. If I've said anything wrong, please let me know in my comments section below. So now let's move on to the last framework, Quick. Quick. The main difference between Quick and the former two frameworks, Svelte and Solid, is that Quick is a server-side rendering as a first citizen full stack web framework. Okay, it's not just a framework. It actually is a full stack. It controls the build and the whole thing when you write. Okay, for Svelte and Solid, it supports both server-side and client-side, but you have but the framework itself focuses on just compiling the component, right? It does not do and you need something else like a full stack framework like SvelteKit to string them together and put server side and client side both together. But you could also just do a client side in Svelte. But for Quick, it's a server side rendering as a first class. It's server side first, and it's a full stack web framework where it controls the entire compilation and build and bundling and everything. Okay, the main goal of Quick is actually to focus on reducing the code needed to be downloaded by the clients, and so that it can optimize the initial page load performance. What quick proposes is no hydration, but resumable. To understand why quick proposes no hydration, let's first understand what is hydration. Typically, when we have both server-side rendering and client-side rendering, our initial page load request always comes to our server, right? And our server-side code will generate a HTML string based on the component that you write, and respond the request with the HTML string, which returns to the browser. When the browser receives the HTML string, it will parse it and display the content based on the parsed HTML. Right? So at this time you will have some. This is the in your browser you'll see a button. And if you want some dynamic and reactive application on the client side, you will then need to load the client side code and do client side rendering. And the first time the client side code runs or renders, it actually does not need to create new DOM elements because they have already been created based on the written HTML from the server side. So the first initial render, what the framework needs to do is to generate a virtual DOM or generate some sort of representation, and so that it can compare and matches the actual DOM with what it knows. And so because by doing that, it needs to know which elements, to get the references of which elements, to know that which one needs to add event listeners and which elements that it needs to hold its reference, so that it knows later on how it needs, so that later on it can use it to update its value when the state changes. So this step, matching elements, attach event listeners, and keeping element reference, is called hydration. Hydration is important because if you click on the button now, what we hope to do happen is that it will reuse the existing DOM elements that has already been built from the server side rendering, and updates the elements directly instead of destroying all the DOM elements and rebuild a new DOM elements from scratch from the client side. So if you observe carefully, in the initial page load, the same piece of code is actually run twice. Right? Once in the server side, we run the same component code, same logic to generate the HTML string. And on the client side, during hydration, we need to run through the same logic again so that we can get the same same structure and so that we can able to know which DOM elements, get the DOM element references and attach event listeners. So it's the same component that we run twice, gets the same input and get the same output, just one on the server, one on the client, so that we can matches, so that the output matches the same DOM structure. And so it's the same code but run twice. And Quick wants to change that. Quick proposes that hydration is pure overhead. What Quick hope to achieve is that once we render on the server side, all the code, all the work that has done on the server side, you should no longer do that and repeat that again on the client side. What Quick proposes is that the same piece of code shouldn't run twice. What it should happen is that after rendering on the server side, it should be able to hand over the result and the work to the client side. And the client side should be able to take over whatever the state or result that is being done on the server side and not do them anymore. So that when the user operates on the client side, the code on the client side should be able to resume the work from the server side directly, know where and how to update the DOM. So this is what Quick proposes, resumability. So let's use the same counter component and see how we implement this counter in Quick. So this is a Quick component. You can see Quick uses JSX, so it feels at home with React, but it's a little bit different, right? The main difference is we have over here two functions, or one function, one attribute that has a $ suffix in them in the name. the dollar suffix in quick is actually a marker for the compiler. Any component with a component dollar will automatically be code splitted and lazily loaded. You don't need to write extra code to handle them. These are all done automatically by quick. So the onClick with a dollar suffix means that the click handler, the inline function with the count plus dot value plus plus, will also be code splitted and lazy loaded. Okay, you don't hear me wrong. That handler function will be code splitted and lazily loaded. So what does that mean? So if based on the counter component, the quick bundler will actually, when it builds, will actually generates two files that relates to the component. One file to be run on the server side and one file to be run on the client side. And that client side file is just a click handler. And as you can see in the code on the right, which is the compiled code splitted lazy loaded code for the click handler, right? You can see the shape, although there's a lot of things that you don't know, but you can see it roughly is the event handler. And because Quick proposes that after server-side rendering, you should no longer need to re-render the component on the client side anymore, which means no more hydration. So there's no more component code, right? There's no more code that says how to build or create that button element. No more of that in the client-side code at all, because no more hydration. Quick thinks that for this component, what it needs to do on the client side is just to handle the click event. So to update the text element. So that is what you need only. Okay, so all the code you need is this click handler to increment the count of value. And also this click handler doesn't have to be downloaded immediately. It is lazily loaded only when you click on the button. But how does that happen? Well, we will have to look into the compile code of the server side and also the compile output from the but it's a bit more complex, so let's not look at the generated code from the server side, but let's focus on the HTML output from the server side, right? So this is after you run the server side code that is being generated, and it will respond with this HTML string. So this is what you get from the response from the server. Again, if you look closely, devils is in the details. First of all, this first part, you can see, if you squint your eyes, this is the HTML for our button. You can clearly see a button element over here, except that there's a lot of attributes. We'll go through them later on. And you also can see that the button is surrounded with HTML comments, which I think it's like some sort of placeholder so that you can locate the button. You can locate the boundary of the button component. And also the string inside the attribute of this on:click attribute is interesting. If you pay attention, you can actually see that this is actually a URL path, right? The first path you can see the app component blah 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 .js is a URL path towards the onClick handler file that was generated on the client side. As well as after the hash, the pound sign, you'll see actually that is the name of the function that we generated in the click handler. See, they match. So on click, in Quick, on the server side, it generates the path name and the function name of the onClick handler and render it into the HTML directly. Right? So on the client side, Quick actually listens to click event globally. And if a user clicks on any element, Quick will check if the element has on:click attribute. And so if the user clicks on this button, it has the on:click attribute, then Quick will add the attribute value and quickly find what is the file that is needed, what is the JavaScript module that's needed to be downloaded, downloads it, and then also knows the function name to be xcall. So it will use this to call the exported function from the imported module. So all this will be done lazily, dynamically, only when you click on the button. So this way, we no longer need to need hydration to attach event listeners. The events. So this is how Quick locates what is the event listeners for each element that is rendered from the server side. But if you think about it, doing it this way, Quick is actually strongly coupled the client-side and server-side build process. Or else how would it know? How would the server-side code knows what the client-side output looks like, where is the file path name, and what is the method name? And in fact, if you're using Quick, you have to use the Quick build tools to build the Quick project. And that's how Quick has this tight control of the whole build process and has this tight coupling between the server side and the client side build. Okay, so now we are able to know to execute the onClick function, right? But if you look at the source code, the onClick uses some state variables. It is using the count star that is created in your component. So how does Quick gets this count variable? Because this is declared outside of the scope of the click handler. How does it get this value? How does it update it? And if we could split the conclick function, if we extract out the count, do we extract the count into our handler as well? And if there's multiple event listeners, how do we ensure that all of this are referring, if they're all referring to the count variable, how do we ensure that they are referring to the same count variable? So this is a lot. There's a lot of questions over here. So let's see whether we can answer them one by one. First of all, how does Quick knows that the onClick is using the count from the outer scope, right? The count is not declared within the handler itself. Well, this we can use static analysis to get this detail. During static analysis, this is not difficult. As like our JavaScript engine or any JavaScript tool, a compiler can actually do this. We can actually analyze what kind of variables that's declared in which. We can determine the scope of each of your functions and determine what variables are declared inside them. This is not difficult, right? But however, on our server side, the count state is assigned to a value, right? When you render. Right? How do we extract this value of the state and how do we pass it down to the client side when the code resumes? Well, in our code example, this is just a very simple case, right? Count is initialized to 1 and it stays as that way when we run the code on the server side. So on the client side, if we reinitialize the count again, it is 1. We can't really know whether it is actually the same or it's actually passed down from the server side. However, if the value of this state is actually being retrieved through an API call, then we will really need to pass this result from this API call in our state down to the client side, because we don't want to call this API call again. We don't want to repeat this work by Quick. We don't want to repeat this work calling API calls again on the client side, right? We don't want to fetch again. So being able to pass down the value of the state from the server side to the client side is very important, and able to refer them is very important on the client side in the click handlers later on. So from the server side rendered HTML output, we can clearly see that the value of the state is actually recorded and serialized into the HTML output, right? So the 1 is actually here. This is the states over here. Okay, and in the code splitted onClick handler, the value will be retrieved through this use lexical scope function. It will get the state of variables that's declared within the scope, and this function will return the same variables for all click handlers. So they are all referring to the same variables and you don't have to worry about the references of the variables, right? And so this is how the value is being passed from the server side to the client side. Server will get the value and then serialize it in the HTML that's finally returned from the server. And the client will use this use lexical scope to retrieve this value out from the server and resume the work from the server, right? Resume the state from the server. But then how again, we now able to get the states, but how again does Quick knows that when we update this, right? Here we're doing count.value++. How do we know that changes this state will need to update the DOM? Well, this again, in Quick, we're using the same idea of signals, right? In Quick, we call it differently, but it is the same concept. It is signals. All states that returns from the use lexical scope is actually signals, okay? But then how does the Quick knows that? So we have signals. We know when it's we can subscribe when it's being updated. But how does it know like which signals needs to map to which elements needs to subscribes to the signals, and how do we know how to update the DOM? Well, that information is actually part of the server-side rendered HTML output as well. The subs array that you can see over here is actually a mapping of each signals to the respective DOM elements and attributes. When I attempt to make the component more complex, you can see that this subs array it feels like a list of commands to tell Quick how to traverse the DOM and how to locate the dynamic DOM elements. This approach is very similar to how Solid traverse the DOM to locate the dynamic elements, and then also it has instructions to say how to update, what to update the DOM, like whether it's a value or attribute or things like that. So this is how Quick able to use signals to subscribe to them and update the DOM elements when you modify the signal values in your click handlers, right? So to put it together, Quick proposes no hydration but resumable, and in order to do that, it split the code into a more fine-grained chunks, not just module level splitting or component level splitting. It also split at the event listeners levels as well, because you probably only need to execute the event listeners on the client side, right? If you don't need to remount the create more counter component on client side, then you just need to get the event listeners. And after code splitting, how does the Quick hand over the work or the state that's done from the server side to the client side? Well, Quick will serialize all the states and the information into the HTML, including what is the state and also where to update the DOM. And so that in the event handlers, we will update the signals, and Quick will know which elements in the DOM is dynamic to need to react to the signal changes and quickly updates them. To be honest, what Quick is doing is far more complex than what I've shown over here. But I'm no expert in Quick, so I am afraid I can't delve more into that. And this is Quick, right? The final summary that we have for today is that we have seen three frameworks in this new wave: Svelte, Solid, and Quick. These frameworks uses compiler to static analyze the code and generate a much smaller code output and a much better runtime performance. The exploration of these frameworks deserve our respects and also deserve us to study them even more. So you might be wondering whether this new wave of frameworks, are they going to replace the incumbent big three frameworks? If you look at the current market share of this new wave frameworks, and the current mainstream frameworks, there's actually a very, 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 very long way to go. Moreover, for the big companies, it does not make sense to rewrite the entire application just to switch over to these new frameworks, right? Because just because it's better than the current stack doesn't mean that you need to switch over. There is other considerations as well. There's maintenance costs and there's also maintenance risk. So at the same time, right? So it will take a while to actually get mainstream, and I don't think it will be replaced by them that easily, right? At the same time, frameworks like React, Vue, and Angular, they have been learning and adopting ideas from these new wave frameworks. For example, if you have been following about Vue's development, Vue is actually working on a Vapor mode, which is an alternative experimental compilation strategy that is inspired by Solid. And by that, the exploration of the new Wave frameworks, the learnings, experience actually spread through our front-end ecosystem, not just by them, also by other frameworks that has adopted this mentality, right? So maybe it does not really matter whether this framework will replace the current incumbent. Of course, privately and secretly, as a maintainer of Svelte, I do really wish that Svelte could be the next mainstream framework. Then I'll have wealth, fame, and power. Well, to be honest, I contributed to Svelte because of fun, so it doesn't really matter, okay? So before I end my talk here, here's a quote from me. Compiler-based framework is the new wave. And my sharing ends here. Thank you for listening.